This talk is called a batch of commit batching. This refers to various ways in which it is possible to essentially amortize the cost of an fsync. That is the operation through which Postgres ensures its durability guarantees. So we'll talk about latency components. Local commit speed is essentially a function of hard disk speed. With the sync rep available in Postgres 9.1, there was some batching of commits occurs due to the fact that when this occurs, the latency between the master and any and the nominated synchronous standby is a very important factor, and it's one aspect where latency is important here. Parallel throughput increases, it won't help us here. So we're seeking to essentially split work among multiple clients to, as I say, amortize this particularly expensive operation. Okay, so we have a quick bit on storage latency here, and corresponding transactions per second. So what we can see here is that oftentimes transaction latency is a bottleneck on certain database workloads. So a latency of about 8 milliseconds is typical on a 7200 RPM hard disk, and during much of the development of Postgres 9.2's group commit stuff, I used my own laptop's hard disk, which indeed had a latency of 8 milliseconds. So much of this information is predicated on, a raw sync latency of that kind of order. As we can see, with very low latency devices, such as flashcards or battery-backed write caches, it's possible to see a massive increase in throughput, as compared to a lower latency device. This graph illustrates the impact of latency on throughput. So it's showing the same disks with and without a battery-backed unit. So that's a fairly dramatic difference. I think it's probably self-evident that the commit speed is highly important here. This graph represents a PG bench workload at various client counts. Synchronous performance. So with the sync rep stuff in 9.1, there's full duplex communication. That is, the confirmation needs to be received by from the synchronous standby on the master before control returns to the client, indicating that the transaction has been committed with the super durability of sync rep. The reply messages have only one write location and are 64 bytes, and they are limited by the network speed plus the while write time. The internet is approximately half the speed of light. Obviously, the speed of light is an absolute limit on how fast anything can go. In fact, here's a speed of light. Light is pretty fast, right? Well, yeah, but not that. It can still be quite problematic. So we have 10 milliseconds latency is common for even close local areas, 3 blocks down, or I get that kind of ping time if I ping Google. 80 milliseconds is about the time it takes to cross the Atlantic Ocean, and if you're going across the Pacific, it's more like 150 milliseconds. Talk a bit about network latency. So here we're highlighting the latency between Baltimore, New York City, San Francisco, and the Netherlands. The Netherlands is kind of pertinent here because last year, myself and Greg over here, my colleague, we discovered, along with our CTO, Simon Riggs, that SyncRep's batching capability, that is its tendency to optimize transaction throughput by minimizing the number of acknowledgements, with a synchronous standby located at Greg's office in Baltimore from his laptop in our hotel in the Netherlands. Anyway, so as I said, the latency there is about 100 milliseconds. So that if you have a single client, the number of transactions a second there is pretty poor, approximately 10. So that's why you will only see this batching effect with multiple clients. So we can do commit batching in various situations in PostgreSQL 9.2. By wrapping multiple statements into one transaction, we need only have one durable write for that transaction. So we need only fsync the write-ahead log for that transaction. It is possible for multiple statements to be grouped into each physical commit. Multiple clients worth of commits can be grouped into less physical commits. This is vital to high latency synchronous replication because, 10 transactions per second is obviously pretty poor performance, and there's no point in, you'd be encouraged to try and add more clients to increase throughput for that reason alone, were you using synchronous replication, or indeed to just do more with single transactions. Synchronous replication implies zero data loss. Of course, the durability guarantees, this can be usefully thought of as going above and beyond the usual durability guarantees of Postgres, because the durable, you have what I've called super durability, which is this property that there's a nominated synchronous standby which has the transaction safely synced to disk in order for you to, and also on the master as well, in order for you to have the transaction confirmed. This is very efficient with this batching. So the important thing about SyncRep, an important property, is that it is controlled at the transaction granularity. Even with this batching effect, it's important that we use this only when we need to. So synchronous replication, although I'm not aware of any other implementations, traditionally it has implied that you could afford to pay for something like a low latency switch, in a trading platform or something like that, because of the inherent expense of this super durability. So one innovation that the 9.1 implementation introduced was that this durability could be, could be opted in. You could opt in or opt out for this level of durability in deference to the actual value of the data to your business. So, for example, you have financial transactions; they would need the super durability, Or you might have instant messaging archives that would, they could go the opposite extreme. And you could have asynchronous commits that might not even be committed on the master, and thus getting a considerable boost in performance and transaction throughput, if that in fact made sense for your particular use case. So that is something we're pretty happy with. But that's in the 9.1 release, not the 9.2 release that's just gone. Okay, so this is the while latency and sync rep test we did in Amsterdam. So Greg had a master in Baltimore. A standby at the hotel, the PGConf.eu 2011, was held at the Castle 400 Amsterdam. The commit rate measured with insert statements, that's a little bit sympathetic because we're talking about very small transactions comprised entirely of a single insert statement. Ping time was put at 100 milliseconds, which we've already said. Typical sync commit time, just over 112 milliseconds. And our theoretical single client max is 10 transactions per second. The measured single client rate was about 7 to 8 transactions per second. So Simon and Greg and myself put our heads together and we wondered how much does it scale. This was in advance of a talk they were giving on synchronous replication, because that was one of the major 9.1 features, which was sort of the hot new thing at the time. And it scales pretty well. So you'll recall that at one client we only had about 10 transactions per second, but we have this sort of, this very impressive scalability as clients are added, right up the way to 300 clients, where it leveled off at about 2,000 transactions per second. Bear in mind, these are special transactions that offer this super durability property across the Atlantic Ocean. So for that reason, this is actually pretty impressive. I'll talk a bit about the local group commit in 9.1. The sync group commit is almost linear with client count. So you get a little bit of a benefit when you increase the client count, but pretty soon it levels off and it gets stuck at a certain point and it just flatlines. So we observed that local commit rates were not doing the same thing as sync rep was doing. So we were in this kind of perverse situation where sync rep was performing better than local commits, under certain conditions at least. They weren't performing as expected. And here's pretty much the graph you see if you try and do this in 9.1. You get to 50, 60 clients, and it doesn't get any better than that. So that's very disappointing, considering we got 2,000 for super durable transactions. Under, with more clients granted, but still. This is a quick. We'll talk briefly about something called commit delay. Now, commit delay is this variable which, quite simply, adds a sleep at a point just prior to the code path where we actually flush while to permanent storage, in the hope of making transactions coincide such that they are committed in batch. This is a graph Greg produced in, I believe, 2007, back when 8.3 was current. And what you're seeing here is utter confusion, really, because it's possible to see little spikes in performance, using this implementation, but there's really sort of no rhyme or reason to it. It defied any kind of sensible analysis. And ultimately, at the time, we determined that it wasn't worth pursuing. There was other sort of low-hanging fruit. So that was sort of left at that. And it was considered to be a bit of a waste of time, because any practical advice you read on commit delay sounded something like, don't use this setting. It doesn't do anything good. It's useless. And I actually tried to have it deprecated, but then I completely reversed my position when I found out a way of making it useful, and I'll talk about that in a minute. This is an example of a counter-tuned insert scaling on 9.1. So I've added quite a large delay here in the hope of getting this, getting this batching effect to occur. Well, this is obviously a contrived example to show you what setting this value at a high value results in. So here we see quite a big drop off in performance. So commit delay was not at all a compelling thing to set, because it was just as likely to hurt performance as help it. And we essentially have been recommending people to not use it for a long time. It's been around for since the 90s. It's a good idea in principle, but what we were doing was just having an independent weight for each and every backend, each and every connection independently weighted, rather than having a coordinated delay whereby their actions were coordinated such that they coincided rather than just having an arbitrary delay. So it just didn't work. Okay. So the write-ahead log disk flush allows for commit batching in PostgreSQL 9.2. So the patch that was ultimately committed that I worked on along with my colleague Simon Riggs and Heikki Lenakangas essentially worked by improving the locking situation in this function where we flush while xlog flush it's called. So so when the function starts, xlog flush checks if others have flushed forward the known. They've flushed a point ahead of the known, or sorry, if their point that they're flushing is behind the known flush point of of the known flushed up to point. So we have this sort of fast path check without acquiring any lock, and it's potentially the function can return at that point, while still being durable because it knows the work's already been done for it. Only one client can flush data to disk at a time, and only one person can call xlog write. So this synchronization occurs with this LW lock while write lock. LW locks are an internal type of lock. They're used to coordinate access to shared memory. So essentially, they're used here to nominate who gets to write while, and indeed to flush it. So the xlog write function updates shared memory, which is why we need this LW lock. So because it's an exclusive lock, only one client can hold it at a time. And this was measured as a heavy bottleneck. And the optimal behavior, as we've seen, is for high concurrency with few physical commits, and the number of commits, the number of people that are actually going through with the flush for themselves should be relatively low. I think I probably haven't explained that very well, so let me just take a step back. So essentially, in the prior implementation, there was, quite simply, there was this fast pass check before the lock was acquired, but then we go to acquire the lock, and we have to wait in a queue. The way things are now, we've got this way of waiting for the lock, but when the lock becomes available, we recheck if our flushed up to point has been reached. And when we recheck, often we'll find that it has. So we're not actually, we're sort of optimistically rechecking rather than just waiting on the lock. The principle is actually quite simple. So in that, by doing that, we greatly decrease the contention on the lock, and at least at high client counts, we get a really dramatic performance improvement for workloads that are commit bound. So myself and Simon sort of took a shot at this first by generalizing the sync rep code so that it was also used in the general case rather than just the sync rep case. But ultimately, as a result of community feedback, an implementation was committed that did this thing with LW locks, which had exactly the same performance characteristics and was somewhat simpler. So we assume most clients will fail to commit when trying to obtain the lightweight lock. We have this idea that the one lucky backend that happens to acquire the lock, that one is conceptually the group commit leader. So that's the one that's driving the process, if you like. That's the backend that happened to get the lock, and on that basis alone happens to drive the commit batching. So, like I said, we expect only a small minority of actual committing transactions to ever make the backend a group commit leader. We'd only need one at a time. So most of the time, as I said, it's spent sleeping. We have this new function, LW lock acquire or wait. So when the lock becomes available, as I said, we don't get the lock. We just stop blocking, and then we try the fast path again. Okay, so in this fashion, it's possible to get hundreds of database commits per physical commit. And by the way, just so, let me be clear what I'm talking about here. This is something you just get. You don't have to turn this on. The commit, yeah, Peter's happy with this. The commit delay thing is something that you're going to have to set yourself, most likely. I'll talk about that in a minute. But this is something you just get for free, essentially, without having to think about it. So this is a graph of insert scaling after the before and after, if you like. And in both cases, we don't have a commit delay at all. So we're just talking about stock PostgreSQL, essentially. And so we see as the number of clients increases, we get this pretty dramatic, performance improvement. The thing is, though, that's only up to 60 clients. And it's possible for it just to keep going, for it to keep getting better and better.
I think it's worth pointing out that the fundamental rate is still like 120.
Right. So we've kind of overcome this fundamental limitation that an naive implementation would have. That is, it would be bound purely by the commit rate, and it wouldn't have any, it wouldn't have any smarts about amortizing the cost among concurrently committing transactions. That's annoying. Okay, so this doesn't have a commit delay. That's something else entirely. And in fact, the last time Greg and I gave this talk, as I said earlier, we were saying that commit delay is useless, get rid of commit delay, and we changed our mind about that in light of something I found out myself. So here's the really dramatic one. So we see upwards of an order of magnitude increase in transaction throughput on a sympathetic workload. This was a benchmark that I did on my laptop earlier in the year. So yeah, that's pretty dramatic. And it now granted, you're probably not going to get this in a real workload, because what we're doing, once again, is we've got many clients that are concurrently executing these tiny transactions with a single insert statement in them. So yes, this is sympathetic, but it's also pretty impressive. Now, one thing we see here is with lower client counts that are perhaps not so representative of the real world, we're not doing so well. So that was actually criticism of what we were doing at the time, but I think we managed to address that issue separately. Sure, go ahead.
So I just want to emphasize something that may or may not be obvious from how Peter's describing this. This is still a laptop that is fundamentally capable of 120 commits per second. That's all it can do. But by batching this stuff so effectively, it's now getting to where it's capable of doing almost 12,000 commits per second. So I mean, this is just regular old hardware, nothing special about it. So instead of adding a battery-backed write cache or something, it's possible to get thousands of commits per second out of just regular commodity hardware. And I mean, that's pretty amazing when the old state of affairs was if you added a bunch of clients, we were happy to see 1,000, which is basically what you're seeing in that graph in the green here.
Thanks, Greg. Okay, this is a little bit more on user selectable durability. That is set via the synchronous commit parameter. So Postgres allows you to trade off, different. I spoke about this earlier, but I'll cover it again briefly. It allows you to make a trade-off, in the level of durability you get from super durable, sync rep on the one hand to a local commit on the other, and most lax of all, you can do an asynchronous commit where we don't block on a transaction being committed. We just return. Now that's quite different from turning off fsync, because turning off fsync implies data corruption. This is a perfectly safe thing to do, provided you don't require actual durability, and you will see a huge performance improvement from doing that as well. Although I suppose it's been made less compelling by this other stuff that I've done. So yeah. Also, can you say something on Simon? Did some stuff on sync rep for 9.2 as well, didn't he? Okay. Okay. So this is the very fact that we can offer this, we can offer this flexibility in the level of durability you have. You can dynamically change this, even during a transaction for that transaction, depending on just how valuable it turns out to be. This is something we're very proud of. It's a world first from PostgreSQL and second Quadrant. And you have all these durability levels coexisting. So you don't have to make that big investment in the low latency switch to get this thing. You just need it. You just use it as you need it and nowhere else. So this is a table sort of illustrating different durability levels. Do you want to talk about this, Greg?
The main point of this table is just that when we go to sync wrap, there actually is an additional new concept here, which is whether or not you worry about committing stuff to physical disk on the master is now a separate concept from whether you commit to physical disk on the replica. There are cases where you may say, well, as long as I get a physical commit on the local side, I'm okay. There were some additional things in here, and they were needed just to make it possible to sort out, am I okay with no actual durable commit? Do I just need a local commit, or do I need one over on the other side? So this parameters got a little more complicated than what we would have liked them to be, but all of these are possibilities, and again, you can pop through them by transaction level and set them when they're appropriate. The point of the chart is to show that you have this many options and you can tweak them, and there's that many of them because each one of them has what we think is a valid use case that people are interested in optimizing for.
Thanks. Okay, so a little bit earlier we talked about commit delay. So just to recap, it's this idea that adding a delay when we go to commit, such that transactions that didn't coincide closely enough now do coincide closely enough, and that we can more usefully commit more transactions at a time. So by actually adding a sleep. So this is controlled by the commit siblings parameter, which is an integer value indicating the number of other transactions that have to be occurring for this delay to actually occur in the first place. So it was presumed that this was only going to be useful at higher client counts, although there's evidence that it will work quite nicely even with 2 clients. So in that situation, some delay is added in the hopes that the commits will batch together. So in 9.2, this is an independent delay. This is something completely orthogonal to the LW lock optimizations that were added in 9.2. So it doesn't really make a lot of sense that we have commit delay at all in 9.2. But then again, it never really did make any sense. But in 9.3, I improved things considerably. Incidentally, older research, and Greg's original observations about this still hold, because the broad trend is the same, which appears to be that about half of raw sync speed, in my particular case, about 4 milliseconds, because I've got like a 7200 RPM drive on my laptop. That appears to be an optimal delay, and it does improve things even at 2 clients in 9.3. So the original code, as I've been saying, it was pretty bad. So in 9.3 we put the commit delay in the best place, and there's synergy with the 9.2 group commit improvements too. So what do I mean by that? Well, quite obviously, okay, so it's called group commit. The operative word here is group. So the delay, rather than just occurring everywhere, only occurs within the leader backend. It occurs within Xlog flush. So at that critical point, when it's holding the lock and every backend that might be committing a transaction is backing up behind the leader, at that point, specifically, we delay. So we accumulate transactions for our leader to actually commit when it finishes its delay and goes on to doing the work that it has to do. And this works really well. So this graph is kind of the same one you saw before. So, okay, the red line is sort of like the one you saw before, more or less. The blue line is what happens if we set the delay of 4,000, which was found to be roughly optimal for this insert workload. And it doesn't do much harm, but it certainly doesn't do any good either. It's possible for it to see, for that particular value to actually prove things with a different workload, but it's contingent upon the actual workload, which is obviously, completely useless because it's just completely impractical to set it. So by delaying within the leader backend, we get this green line. So it's pretty good on. I think it's good to ignore this part of the graph. Look at this part of the graph, because this is actually much more representative of the real world. How many people have more than 100 concurrent? Okay. Well, okay, some people do, obviously, but I think it's fair to say that people with less than 100 clients are more representative of the real world than people with more. workloads with more. So on those workloads in particular, this, we got like about a 70% increase in throughput, again, above and beyond what we have in 9.2. So yeah, that's pretty nice. But perhaps more importantly, this particular setting continues to be effective with TPC-B. So this is a TPC-B benchmark. Now this is a completely different benchmark where each transaction has, I think, 5 statements. One of them is a select statement. So this is a totally different workload, and yet the delay appears to continue to be optimal. So the indication is that there is some science to this thing now. We have some hope of setting the delay in a way that is generally optimal. Because, of course, each backend isn't independently waiting. It's only waiting for as long as it has to in order to flush, and no longer. Okay. Futures. I've been spending a lot of time trying to figure out a way of making the commit delay thing adaptive. I'm having a really hard time beating my original observation, which was, I independently made the same observation as Greg did back in 2007 about this half raw commit time being appearing to be optimal. I'm having a really hard time beating my best there by having an adaptive implementation that perhaps instruments sync time in real time, which might be more suitable for cloud environments. So it remains to be seen if I'll be successful in making it adaptive and how much more useful that can be. This is something we've mostly tried out with synthetic workloads, and as we've seen, it works great there, but I think we probably need more experience in the field before we can really confidently recommend any particular course of action. But so this is very much an area of ongoing research. Although the commit delay thing, it has been committed to 9.3, so it's all very good. We haven't yet looked into workloads that have fast commits. So very earlier on, we saw that there were some commit speeds that were much lower for things like battery-backed caches, and SSDs also have considerably faster fsyncs than traditional spinning Rust. But there is apparently some benefit to be had from a small commit delay, even in that situation, when there are many clients. Okay. Conclusions. Battery-backed caches will help performance considerably for local systems. Wide area network overhead during sync rep is dominated by the speed of light. Obviously, that's the that is in fact a speed limit on how fast that can occur. Group commit really helps with multiple clients. In 9.2, there are big improvements in the sync rep and local cases. And the 9.3 commit delay changes will help further. We need to only flush what's necessary, and applications need to be aware of durability, at least to get the most benefit from this sort of family of techniques, specifically with regard to dynamically changing durability setting. Greg, any? Okay, I think we're done. I'll take questions. Okay, Peter?
Yeah, so first a comment.
Yep.
The workload that you describe as synthetic and not realistic is exactly the workload of a large-scale web application. Every large-scale web application has basically that exact design, which is people do stuff, and then it writes a table into a row, and that's how it works. And there are
great.
So this is far from irrelevant.
Well, I think that I suppose my point was just that sort of the dizzying highs seen at sort of 300 clients. You know, it's not like it's going to get 10 times faster, but it might.
So it's also interesting.
Yep.
Conventional Postgres wisdom is don't run a lot of backends.
Yep.
This seems to basically shake that advice pretty dramatically.
Mm-hmm.
We've seen in production that people actually running more backends see much more throughput in our operations. We certainly don't advise people to run only 10 backends. We have many customers running 100 on a server without problems. Would you say that the benefits of this kind of commit batching might outweigh the traditional benefits of running fewer? I mean, maybe Greg's a better person to ask this.
Yes, he sure is.
He has stronger opinions on the old way.
Yeah, so I mean, the sort of spots where the connection limits started to become problems for people were normally up in the people are using 500 or more clients. There starts to be some internal contention for resources that make that less effective. If your goal is to optimize CPU-bound queries, then keeping a very low connection count does that better than many other approaches. So systems that fit all of their data in RAM, you can basically prove that those will run faster with smaller amounts of clients. But the case you're talking about is neither of those. You're talking about the data is being written out regularly. There's a large number of clients involved. They're not CPU bound. You know, so I think going up into the small number of hundreds for client count in hopes that you get more of this group commit behavior is completely sensible if you're in an environment where optimal CPU performance is not your limiter anyway. You're trying to get as much disk I/O as possible out of it. But you still don't want to go up into like the multiple thousand range simply because there are still some bottlenecks within Postgres that make that kind of hairy and cause locking issues.
So the other question is, can you comment a bit on how you arrived at 4,000 millis or what, micros?
Yes, 4,000 microseconds, 4 milliseconds.
I guess, like, is it very sensitive? If you double it, if you half it, like, you said you tested a bunch of stuff.
I did,
You
yep.
only showed the one.
Right, the good one. Yeah. Yes. So if you put it at sort of 3,000, it's not quite as good. If you put it at 5,000, it's not quite as good. And I think it sort of tends to fall off when you get past, say, 10,000. There isn't. I don't have a whole lot of theoretical. I don't sort of have a mental model of why that should be. That's particularly detailed.
Well, presumably if you delayed for like an hour.
Well, yeah, exactly, yeah. That's just been my observation. I'm attempting to, as I've told you, I'm attempting to make the thing adaptive, and I'm actually reading some academic papers that might be helpful in this regard. So how I actually got that number was, so this contrib module, it's called PG Test Fsync. It's a standalone program. You run the program for a set number of seconds, and at that point, you get a raw sync time. So you get a number of operations per second, I think, and you use simple math to figure out what the average sync time is, and you half that. So that's how I arrived at 8 milliseconds and 4 milliseconds. And this does appear to there does appear to be a pattern to this, but it's kind of a hard problem to analyze because there's so many moving parts. But I think it's probably doable, and I think I'd really like to just get it so that people don't have to think about it. They press the button and they turn it on, and that's it. And it appears that it's possible to do that with other relational databases. So I hope to, be able to offer that. So it's something I'm hoping to get done in the next couple of months.
Yeah, the older test that I did, there was definitely a kind of a local maximum in a broader area that was still helpful. Like Peter was just saying, 4,000 was best, but 3,000 or 5,000 were still significantly better than nothing. So, I mean, it's not like it was you got to get it exactly right. I think it is going to be one of those where there's a reasonable range for it, and you might even be able to set it from first principles and then just be done with it and probably get it right. It's not going to be one of those really finicky, it has to be exactly right, or it's of no help sort of parameters based on what we know so far. And the results Peter is getting now are even less kind of bizarre and non-correlated trends than when I was doing this before. So I'm hoping it cleans up really nicely now.
That's really the underlying, that's the major advantage of the commit delay stuff. It sort of starts to make sense now, because the really kind of inconsistent results we saw before were presumably because of, serendipitous timing, where someone happened to be able to successfully batch stuff, because there had to be someone to do the batching. So it was all just sort of happenstance as to whether or not this, this actually occurred, and there was no particular science to it. It was just random. Does that?
I think we're all done. Thank you, Peter.
Thank you.